I think it's this. Oh, there you go. You can all hear me well? Yes, hi, I'm Stefano. I work in diagrammatic methods for quantum computing and other things. For the second part of this talk, I'm going to give you a very brief overview of what has been achieved using the ZX calculus and variations in terms of quantum circuit optimization, which is ultimately what we want to do in order to be able to run these one-shot signatures as soon as possible. So we want a circuit that's as small as possible in terms of number of T-gates, T-depth, other quantities, number of entangling gates, and so on, depending on what we optimize for. Fabrizio has already presented this. These are the basic ingredients of the ZX calculus. If you come from, say, tensor networks community, or you've done tensors, these are just tensors. So you can think of them as tensors, you can think of them as linear maps in the Dirac notation, however you prefer, it doesn't really matter, they're the same. And the important thing is indeed that we have some rewrite rules that are guaranteed to preserve the meaning of the tensor networks. So whenever we apply one of these rewrite rules, we get a different tensor network that represents the same tensor. So really you should think that a computation is one giant state, hundreds of qubits, potentially thousands of qubits in our case, and you want to take that description of a state and rewrite and rewrite and rewrite until it becomes shorter or simpler or cheaper to produce. That's the idea. You can use these rules, and anything derived from these rules, you're guaranteed that you will get a state that's equivalent. But perhaps it gives you a better way to produce it, so a shorter algorithm or a cheaper algorithm, something like that. And indeed, that's what has been done in the field. Now, different kinds of quantum computing have different notations. Probably most people are familiar with quantum circuits, in which case that's how you write the basic gates of quantum circuits in the ZX calculus. That's already what Fabrizio showed. The difference is that the C0 is now not just a symbol that sort of indicates that one part is connected to the other. No, it's actually two tensors. It's a factorization of a four-leg tensor into two-leg tensors contracted in the middle. So it tells you that the C0 really has less degrees of freedom than you'd expect. So you can simplify it further. You can just simplify one bit of it and leave the other bit there. It's a copy and XOR if you want, closer to the classical version. But if you do fault-tolerant quantum computing, then you might be into measurement-based quantum computing, which is a different way of writing equivalent programs. It's good to know that the ZX calculus also helps with MBQC. So you can translate the ingredients of MBQC into ZX diagrams, and this is used for some optimization techniques later on. If you do quantum error correction, then it's also good to know that the ZX calculus helps to write CSS codes, so error correcting codes. And you can do surface code lattice surgery with the ZX calculus. It is a very popular way of formulating computations in error-corrected regimes by thinking of many, in this case 9, but typically hundreds or thousands of physical qubits as one logical qubit. There are many qubits. You just use a very, very entangled state, or to be precise, a very, very entangled subspace of dimension 2, and that is your logical qubit, which is really spread across these hundreds or thousands of qubits in such a way that is error resistant. And then you don't want to think about the computations as circuits on 9 or 100 or 1,000 qubits. You really want to think of these computations in terms of logical operations on the logical qubits. And it turns out that people discovered this a few years ago. Dominic Horstman introduced it originally with collaborators, and then this was rediscovered and redone by other people working in lattice surgery. But really, the four basic operations that are performed on these lattices to get all kinds of circuits, all kinds of algorithms, are just the generators of the ZX calculus, plus minus some error correction. So the ZX calculus is really a natural language for the most popular way, the most popular path forward for fault-tolerant quantum computing today. So this is a pretty important observation to make. Now, there's two main references. These are technical references. One is a paper by John van Wettering, and the other one is a big, very thick book, which is called Picturing Quantum Process, which can be used as a book to learn, or if you're camping, you can use it as a log. You can build things with it. You can chop it for fire. I mean, it's really a multi-purpose book. But three main things that you can do with the ZX calculus, just a brief overview of the literature, if you will. There are references, so if you want to learn more, I suggest you go and read one or two of these papers just to get a feel for how the things are done in practice. The first and most important one is T-count reduction. Now, in fault-tolerant quantum computing, the cost is not really the number of gates, it's the number of T-gates. So there's a special kind of gate that's hard to do. The other ones are all very cheap. T-gates are the ones that ultimately determine how many hours, days, weeks, months, years your computation will take on a fault-tolerant quantum computer. So we want to reduce them as much as possible. Here's an example from an early paper that shows a reduction by about 33% on a small circuit. And the way that this works is really that you take a circuit, you expand it into a ZX diagram, you apply these rewrite rules to make it into a big jumble. This jumble is smaller, actually. You simplify the jumble, and then you extract the circuit back. And the circuit that you extract is typically simpler than the original one, if you've done your job well. And this is the kind of rules, this is the kind of patterns that one uses. I don't really need to get into, but they're all graph rewrite rules. You think of these as graphs with colors and some annotations, and all you do is you look at the neighborhoods of the nodes, find some small patterns, and apply simplification rules until you can simplify no more. And then you say, okay, I'm done. How did this go? And you check how it went, and you build, typically these papers end with tables that compare best previous reduction counts to the best new counts, and you can see, well, in this case, this was one of the earlier papers. All of the black entries on the right column are circuits where this technique outperformed the previous best, which was not graph-based. And in fact, this is a result that comes again and again in this kind of research. These techniques outperform by 10, 20, 30% other techniques that existed before and other compilers that are being developed now. They're extremely effective, they're extremely parallelizable. So some things that you can do is you can derive some identities. So you look at slightly bigger circuits and you say, okay, this sub-circuit appears a lot. I see this pattern again and again and again. Can I make it better? Can I simplify it? And so you find patterns such as that one, which looks like complicated, but in reality, if you do your calculations, that's just identity. All of those cancel out. And it turns out that these patterns appear as a sub-pattern in many, many, many other bigger circuits. So what you can do is you can rewrite your basic building blocks in a way that is friendly to that pattern, that makes that pattern appear often. And then you fuse them, compress them, and then you look at that, and every time you find it, you just remove it. And you see how that does. Maybe that strategy doesn't work, maybe it does. It turns out, again, in this paper, outperformed, what, 80%, 75% of previous techniques? Again, just rewrite things in a simple form, look for a pattern that you know how to remove or how to simplify it, mix some of these techniques together, like you run one, then you run a second one, you run a third one, and you see how it goes. And it tends to do pretty well. Now, that's for simplification, but of course, we're not just interested in running the circuits. This is early days. We also want to, simulate them on our laptops. Most of our quantum computers are not very good today. They're noisy, they're definitely not fault tolerant, so we still want to run simulations of fairly large circuits in reasonable time to get data, for example, to get thresholds or to see what collision probabilities we get out of our functions. So another interesting avenue of research is how do we simulate circuits faster? Now, this has always been sort of a bone of contention between different communities. There's a famous quantum supremacy paper by Google, used a very specific model of simulation to make their 10,000-year claims. 2 years later, the same circuits were simulated, so perhaps the 10,000-year claims didn't age very well. But indeed, that's the point. Depending on how you simulate your circuit, depending on how you look at your circuit, you get different results. So if you think of it as I have a big state and I apply gate by gate by gate, that probably takes a long time. But if you think of it as a big tensor network and you contract it, then maybe that's faster. If you don't even contract it, but just simplify first, you simplify as much as you possibly can and then contract at the end, maybe you outperform existing techniques. And indeed, that's what one of these papers did a couple of years ago. For example, you observe that the hard things to compute are the T-gates, because the parts that don't have pi over 4 angles, so the parts that only have pi's or pi over 2's or no angles, those are Clifford. So there's a very fast, efficient classical algorithm that simulates the result of your quantum circuit. So the really hard part is whenever you see a pi over 4, that means you have a slowdown of some kind. If you can remove the pi over 4, perhaps by branching, by generating multiple copies of your circuit, but those circuits are still much, much faster to run, then it's worth doing. And indeed, that's the BSS decomposition. That's one of the early observations, is that you can remove, if you find 6 of these pi over 4s, you group them together and you can just remove them at the price of having to run 7 different calculations. So you have to run the same circuit 7 times now, but your circuit is significantly easier to run. In fact, it is 32 times easier to run. And you can do this, again, you look at your graph, big graph, hundreds of thousands or millions of nodes, but we have GPUs, so we can do these things faster. You apply basic pattern rewriting techniques to try and reduce the part that you can reduce. And then you're only left with these dangling gates, and wherever you see these dangling gates, you group them into 6 and remove them, and then have to do 7 calculations. You get a lot of branches, but ultimately you spare some time every step, because you go from 32 to 7, which is a pretty good improvement. And so it turns out that the speed up that you get by doing this decomposition plus the rewriting techniques that simplify your circuit is in the order of factors between 5 and 40, something like that. So this is the non-naive version. Obviously, there's also the naive version, which is how much speed up do I get compared to someone who doesn't know the ZX calculus at all and just tries to simulate the calculation, but that's a bit unfair. It's like, yeah, we know. The question is how much speed up you get more with this technique, because they're composable, as I said. And you can do better. You can look at more complicated patterns. So there's a follow-up paper that just says, oh, look, these states appear a lot. Again, you look at practical examples. That's always the source of insight. You look at practical circuits and see patterns that repeat and think, oh, maybe this pattern can be simplified. And you put a couple of PhD students to work on it, and 6 months later or a year later, you get a small prototype that does it, maybe. And then you run it, and you discover that, for example, the algorithm that you taught the year before was really nice, gave you a like 40x speed up. Well, now you can do 10x better. So you get like a 400x speed up compared to previous techniques, just by adding one more observation to the mix. And you just do this more and more. It feels very combinatorial. It feels very ad hoc, but it works, which is the only thing that we care about. Really, we just want to be able to run these circuits as fast as we can. We don't care how. It's dirty, sure. So as a final point, these diagrams don't necessarily look like circuits, and indeed, after you start rewriting them, they definitely don't look like circuits. So yeah, great, you start with a circuit, turn it into a diagram, you know how to write a circuit from that, but then you rewrite it, you get a big graph. What is the circuit associated to that big graph? How do you run a graph? Well, you don't run the graph, of course, but you have to synthesize. You have to extract the circuit back from it. It turns out that extracting a circuit in general is hard, but extracting a circuit when you have obtained the diagram by preserving certain flow properties, a certain causality, so you know effectively which edges carry the original qubits in a sense, in a very vague sense. So if you do MBQC, forgive me for putting it this way. Then you can synthesize the circuit more efficiently afterwards. And indeed, some of these techniques just do that. You take a big graph, you think of it as a measurement-based pattern, and then you apply a bunch of rewrite rules, simplify it so that you have just finitely many simple cases that you have to handle. And then from those simple cases, you know the pattern to extract a circuit. So you say, my circuit is now in a standard form, and I apply a deterministic algorithm that just looks, say, at some working frontier and starts pulling out quantum gates from it. So you have a big blob on the left, and you pull out gates because you know the format of that big blob. You start pulling out the quantum circuit gates one by one until you get a circuit that does the same thing. So you get an equivalent circuit this way. And indeed, this kind of extraction techniques are used by Quantinuum specifically to do some of their compilation steps. They turn things into graphs, simplify the graph, extract the circuit back, and that typically gives you much better circuits, much shorter circuits. And just as a brief, conclusive, wrapping up note, I promise, Fabrizio mentioned that we can do AI. Indeed, there's recent work on reinforcement learning for this, which doesn't yet perform quite as well as the deterministic sort of algorithmic techniques, but gets close. So now that we have more computational power, the more computational power we have, the better these techniques are likely to perform. So we will probably see more of this in the coming months and years. And a brief mention that if you're specifically interested in oracles, so classical oracles, such as those coming from hash functions in Grover, then there's specialized versions of the calculi that make it easier to write some of those primitives. So such as the Toffoli gates or the N gates. These are called the ZH calculus and ZXN calculus. These are equivalent. You can translate from one to the other, but sometimes it is easier to have a notation that makes it just more straightforward to say, here is my Toffoli, and my Toffoli just consists of 3 bits that are logically relevant to me. That's pretty much it. I think this was a fairly comprehensive overview of the current state of things in simulation and optimization using these diagrammatic methods. It's lunchtime, so we'll wrap up, but we can have a chat about it later or during lunch. And for now, thank you.